When you look at the moon from Earth, you see a dead world. Ancient craters, seas of lava solidified billions of years ago, absolute silence. It's beautiful in its stillness, but geologically, it's dead. It has been dead for eons. And we naturally assumed that's how all moons are. Cold rocks orbiting planets, silent witnesses to the cosmos, without activity, without geological life. That assumption shattered on March 9th, 1979. That day, the Voyager 1 probe captured images of Io, Jupiter's innermost moon. Linda Morabito, a navigation engineer at the Jet Propulsion Laboratory, was processing images to track the spacecraft's trajectory when she noticed something strange at Io's edge. A giant plume rising 280 kilometers above the surface. At first, she thought it was an error, perhaps another moon behind Io. But it wasn't. It was a volcanic eruption, an active volcano on another moon. And it wasn't just one. Voyager discovered 9 active volcanic plumes on that first flyby. Later missions revealed the full truth. Io has hundreds of volcanoes, more than 150 erupting constantly at any given moment. It's the most volcanically active object in the entire solar system. Earth, with its plate tectonics and molten core, has approximately 1,500 total volcanoes, most of them dormant or extinct. Io, a moon the size of our moon, surpasses Earth in volcanic activity by orders of magnitude. This doesn't make sense. It shouldn't be possible, and yet it exists. The anomaly that shouldn't exist. To understand why Io is so impossible, you need to understand something fundamental about geologically active worlds. Volcanic activity requires internal heat. That heat can come from 2 main sources: radioactive decay of elements like uranium and thorium inside the body, or residual heat from the planet's formation that hasn't fully dissipated yet. Earth has both. Our core still retains primordial heat from when the planet formed 4.5 billion years ago, and radioactive decay in the mantle constantly generates additional heat. That's enough to keep our outer core liquid, drive plate tectonics, and fuel volcanoes. But Io is a moon, not a planet. Moons are smaller, they cool faster. Our moon lost its internal heat more than 3 billion years ago. Europa, another moon of Jupiter, probably has a subsurface ocean maintained by tidal heating, but it has no surface volcanism. Titan has cryovolcanism fed by complex internal chemistry. But Io is different. Io has molten rock volcanism, real lava, temperatures exceeding 1,500 degrees Celsius. Some eruptions reach 1,600 degrees Celsius, hotter than any terrestrial volcano today. Where does all that energy come from? Jupiter, the giant destroying its own moon. The answer lies in the gravitational monster that Io orbits every 42 hours, Jupiter. Jupiter has a mass 318 times greater than Earth. It's so massive that its center of mass with the Sun technically lies outside the solar surface. When something orbits Jupiter, it doesn't just orbit. It gets stretched, compressed, deformed by immense tidal forces. Io orbits just 421,700 kilometers from Jupiter. That's barely a bit farther than the distance between Earth and the Moon. But Jupiter is vastly more massive than Earth, which means the tidal forces on Io are brutal. The side of Io facing Jupiter experiences significantly stronger gravitational pull than the opposite side. This stretches Io as if it were clay. If Io had a perfectly circular orbit, and there were no other moons interfering, it would eventually become tidally locked in a stable configuration, always showing the same face to Jupiter without additional deformation. Tidal heating would stop. Io would cool. It would become geologically dead. But Io isn't alone. The orbital resonance that amplifies the chaos. This is where the story becomes truly fascinating. Io is trapped in something called a Laplace orbital resonance with Europa and Ganymede, the other large Galilean moons. For every orbit Ganymede completes, Europa completes 2 and Io completes 4. A perfect 1 to 2 to 4 resonance. This resonance means that every time Io tries to circularize its orbit and stabilize, Europa and Ganymede gravitationally push it back into a slightly eccentric orbit. Io's orbital eccentricity is barely 0.0041, tiny compared to eccentric planets or asteroids. But it's enough. It's enough for Jupiter's tidal forces to vary throughout each orbit. When Io is at its closest point to Jupiter, periapsis, the gravitational pull is stronger. When it's at its farthest point, apoapsis, it's weaker. This variation causes Io to constantly deform. It's not a static deformation, it's dynamic, rhythmic, unceasing. Io deforms up to 100 meters vertically each orbit. Imagine that. A solid rocky body flexing 100 meters up and down twice every 42 hours, eternally. That flexing generates massive internal friction, and that friction generates heat. A tremendous amount of heat. Enough to melt rock. Enough to keep hundreds of volcanoes erupting non-stop for billions of years. Gravity, something we normally associate with attraction and stable orbits, becomes an energy source as powerful as radioactive decay or stellar heat. A world that constantly melts. So what is Io actually like? What kind of volcanic inferno does tidal heating create at this scale? Io's surface is an alien landscape of impossible colors. Bright yellows, intense oranges, deep reds, sulfurous whites. All of this comes from the sulfur and sulfur dioxide that dominate its surface chemistry. When sulfur heats to different temperatures, it changes color. Cold sulfur is pale yellow, hot is red, molten is black. Io is a chemical palette in constant flux. Io's volcanoes aren't like Earth's. They don't build the typical volcanic cones we associate with Vesuvius or Mount Fuji. Instead, many eruptions are effusive, with lava flowing in layer after layer over the surface, creating extensive volcanic plains. Resurfacing rates are so high that Io literally renews itself completely every million years or so. There are no visible impact craters on Io. They've all been buried under fresh lava. One of the most famous volcanoes is Loki Patera, a lava lake more than 200 kilometers in diameter. To put that in perspective, it's larger than the state of Connecticut. It's not a cone. It's a giant depression filled with molten rock that periodically churns, with solid crust sinking and fresh lava erupting in regular cycles. Astronomers can predict its eruptions by observing its infrared signature. Explosive eruptions launch material hundreds of kilometers high. On Earth, the most powerful volcanic eruptions reach tens of kilometers. On Io, with its low gravity, only 1/6 of Earth's, and extreme internal pressures, plumes reach heights that would make Krakatoa look like a firecracker. Io's lava is ultramafic, extremely rich in magnesium and iron, similar to the lava that covered early Earth 3 to 4 billion years ago. Studying Io is like observing a window into our own planet's geological past. the atmosphere that appears and disappears. Io has an atmosphere, but it's not an atmosphere like Earth's, stable and permanent. It's ephemeral, a ghostly existence that appears and disappears depending on conditions. Io's atmosphere is composed mainly of sulfur dioxide, sublimating from frost deposits on the surface. When the sun illuminates a region, the frozen SO2 vaporizes, creating a thin local atmosphere. When that region enters Jupiter's shadow during an eclipse, temperatures drop drastically, and the SO2 freezes again, collapsing the atmosphere within minutes. It's an atmosphere that breathes. It inhales and exhales with day and night. And in that process, it reveals something fundamental. Io is so dynamic, so active, so alive, that even its atmosphere can't remain stable. Here's a question to pause and reflect on. If gravity alone can generate enough heat to melt rock for billions of years, what other energy sources might we be completely overlooking in our search for habitable worlds? And could there be moons out there, even more extreme than Io, that we haven't discovered yet? Mountains on a melting world, the tectonic paradox. Here's something strange you wouldn't expect. Io has mountains, many mountains, some over 10 kilometers high, taller than Mount Everest. But wait, if Io is constantly resurfacing with lava, if its surface renews every million years, how can mountains exist? Why aren't they buried under volcanic flows? The answer is that they're not volcanic mountains. They're tectonic mountains, massive blocks of crust that have been pushed upward by tectonic compression. Io's surface, despite being constantly covered by new lava, is also being compressed by tidal forces. That compression creates tectonic stress, and that stress forms mountains. Steeple Mountain, for example, rises more than 10 kilometers above the surrounding plains. It's not a volcano, it's a crustal block lifted by pure tectonic forces. It's as if Earth had plate tectonics without plates, compression without expansion, mountains without roots. Io is a world that defies the geological categories we use to classify rocky planets. The magma, ocean myth and Juno's revelation. For decades after Voyager's discovery, scientists assumed something reasonable. With so much volcanism distributed across Io's entire surface, there must surely be a global magma ocean beneath the crust. A sea of molten rock enveloping the entire interior, feeding volcanoes from below like an infinite lava fountain. The models supported it. The observations didn't contradict it. It became the accepted paradigm. But then Juno arrived. The Juno mission, which has been orbiting Jupiter since 2016, performed extremely close flybys of Io in December 2023 and February 2024, approaching within 1,500 kilometers of the surface. These flybys allowed scientists to measure Io's gravitational field with unprecedented precision. And the gravitational field reveals the internal mass distribution. The data were surprising. There is no global magma ocean. Instead, Io has localized magma chambers, enormous but discrete, concentrated beneath the main volcanic regions. Tidal heating isn't uniform throughout Io's interior. It's asymmetric, chaotic, concentrated in certain zones where orbital geometry and the mantle's rheological properties create hotspots. Io isn't a molten body wrapped in a thin crust. It's a mostly solid world with giant pockets of melted rock that violently explode toward the surface when pressure builds too much. This discovery rewrites our understanding of how tidally heated worlds work, and it has enormous implications. Io as a window to a universe of impossible worlds. So what does all this mean? Why does it matter that a moon of Jupiter is volcanically hyperactive? It matters because Io shows us that habitability, or at least geological activity, doesn't require being close to a star. It doesn't require a massive planet with internal radioactive decay. It only requires the right configuration of gravity, orbital resonance, and tidal forces. And how many such systems exist in the universe? We've discovered more than 5,700 exoplanets. Many are gas giants, hot Jupiters, super-Earths. And those planets probably have moons. If those moons are in orbital resonances similar to Io's, they could be experiencing extreme tidal heating. They could be volcanically active. They could have subsurface oceans maintained by that heat. Worlds orbiting gas giants in their stars' habitable zones, heated not just by starlight, but by the gravity of their host planets. Exomoons with active geology, dynamic atmospheres, complex chemistry, all powered by tidal forces. Io isn't an anomaly. It's a prototype. It's the proof of concept that the universe can create active, complex worlds using mechanisms we're only beginning to understand. The universe doesn't follow our rules. There's something profoundly humbling about studying Io. It reminds us that our intuitions about how worlds should work are limited, based on our experience with Earth and our immediate solar system. We assumed moons are dead. We assumed volcanism requires radioactive decay. We assumed you need to be close to a star to have energy. Io destroys all those assumptions. It shows us that gravity can be as powerful as a star, that orbital resonances can create thermal engines lasting billions of years, that a world the size of our moon can be more geologically active than the entire Earth. And if Io can exist, what else is possible? What other impossible worlds float out there, defying our categories, breaking our rules, showing that the universe is infinitely more creative than we are? Every image of Io, every mapped eruption, every piece of Juno data is a reminder that we're barely scratching the surface of what the cosmos can create. And that, more than any specific discovery, is what makes Io so important. It's not just a volcanic moon. It's an invitation to reimagine what's possible, to accept that the impossible is simply what we haven't seen yet, and to keep searching. Because if the universe can create Io, it can create anything. What other impossible worlds do you think might exist in the universe? What would be your favorite place to explore if you could send a probe to any moon or exomoon? Leave your thoughts in the comments.